All right, so we are on. So yeah, everyone, welcome back to this the second session of this course. Without further ado, I will hand over to Rakvi. Rakvi, the floor is yours. To everyone else, enjoy the session, and I'll see you next time.
Thank you so much, Bambode, and yeah, thank you everyone for coming again. So this, as mentioned in the syllabus, for next couple of lectures, we'll just talk about fields and basically how to do arithmetic on it. So before talking about this field, I would just like to take the opportunity over these two lectures to talk a bit about groups and rings also before talking about fields. So let me start with talking about groups. What do we mean by them, and why are they? Why do we care, and things like that. So, before even giving like a mathematical definition and just a list of properties, I want everyone to just see some examples. Okay, so let's uh, let's take a sort of nice example that I'm sure everybody is familiar with. Let's take the set of integers, which I'll denote by z, which are basically your counting numbers and negative numbers. So 0, 1, 2, 3, 4, 5, 6, and -1, -2, -3, -4, and everything. If you think of this set along with this operation, addition, so immediately there are few things that like everybody is familiar with. There are few things that come to mind. So first of all, so what do I mean by this bracket? So I'm thinking of a set of integers along with operation of addition defined on them. So what it means in particular is that if I give you two integers, you can obviously add them and you will get another integer, right? So this property, so we can add two integers to get another integer. So in particular, what it says is just to write it down mathematically. So you take two integers, so z cross z, and you get another integer, right? Via this map of addition. So if I give you m comma n, m plus n. So this map is defined like this, right? From two integers to another integer. This property is what we will call closure. So that means that operation is well defined. So within your set, you take two numbers and you get another number that is a member of your set. So you're not, so I'm not going outside integers, right? Uh, Second thing that we observe is that there is a special number called zero, right? So there exists zero, right? And what is so special about zero? The special about zero is that if we take any integer m and add 0 to it, we get back m itself. And obviously, this works both ways, right? So this is what we call, this element is what we call identity. So this is identity of our operation, right? So adding, so like performing operation with identity is doing nothing to your element, basically. Third thing is, so if I give you any number, let's say 1, right? So corresponding to that, there is another element such that when you add those two things, you get back 0, right? So like for example, so for an integer m, there exists something called minus m, such that m plus, so that when you add these two things, you get back 0. And again, this works both ways, right? This property is called inverse, generally speaking. So that means that every element has an inverse with respect to that operation that we are considering. And it's okay, let me finish first of all stating what I want to state, and then we'll go into talking about details. And last thing, of course, is what is called associative property. So associativity. Uh, what it means is that order of operation doesn't matter, right? So if I give you three numbers or three integers, let's say m, n, and p, so it doesn't matter whether you add n to p first and then add it to m, or you add m plus n and then add everything to p, right? They all are same. So basically, brackets don't matter for us. These four, so generally, so a group, abstractly speaking, so to say, so just to give a definition, a group G is a set of elements together with an operation. Let me just call that operation, let me just give it a name. See, I don't want to call it addition because, as we will see, there are other operations apart from addition, right? So let me just give it a generic label. Let's just say star. Okay. So it's a set of elements together with an operation. And please keep this example in mind, integers with addition, right? Such that the following properties hold. So first, so which are the properties? These three properties, right? So closure, which means that this map is actually well defined within G. So you take two elements of G, you compose it using this star, and you get another element of G. And then again, just go back. So identity exists, inverse, and then associativity. So identity exists for, so corresponding to every G, corresponding to every element of this set, there is an inverse. And let's give this identity a name, say small e. Like we had 0, so let's just give this a name, small e. So there is an inverse, and let's give this inverse also a name. Let me call it Z inverse. Okay. And then also star is associative. Now, like on the surface, it does seem like we are just like, why do we care about these properties, and why, like, what if we don't have one of them? Don't we get something interesting? I mean, so let's take an aside for a moment and think about some examples where some of these properties fail, right? So, and these examples are not really hard to find, like like we had integers, like we can also think of natural numbers. So now we only have positives, 1 2 3 4 5 6 7. We don't have negative numbers. So what goes wrong with them, right? I can define, let's stick with addition. Let's stick with addition. So I take two natural numbers and you add them and you get another natural number, right? So this operation is also well defined on it. And obviously this addition is associative, because when you're adding positive numbers, the order of addition doesn't really matter. So what do we lack in this set? What do we really don't have? Well, first of all, we don't have identity. Because if we only have positives, 1, 2, 3, then really you can't, I mean, there is no zero, right? So we can't, so there is no number such that nullifies your operation in some sense. So identity is missing. And if we talk about inverses, so we don't have negatives, right? So there are no inverses either in this set. So another way to think of integers for some sense is if we start with natural numbers, and if we want to include some natural things, like for example, borrowing, let's say, or subtraction, then we do end up with Z, right? And that forms a group. Uh, Another, let's same set. Let's even stick with Z, for example, and let's change the operation slightly. Let's think about subtraction, right? This is also a well-defined operation. So, like if I take two integers, I subtract, I get another integer. So this is a binary. Like this operation gives me closure, right? And again, but what do I don't have in this? Um, let's see. So what about associativity? So if I take three numbers, let's say M and N P, then is it true that really the order does not matter? It's not true, right? If I am dealing with subtraction, then I really have to keep track of my brackets, right? Because these two things are not same. So that's one technical. So I don't have associativity, right? What about identity? If I want to have an element such that M minus E is M, then obviously you would say that why can't we take E to be 0? But then I also want E minus M to be M, but that doesn't work, right? So there is no such element E. So no such E. So we don't get identity. And we don't have identity, right? So it doesn't really make sense to talk about inverses either. So then it's I mean it's not like if our set and operation don't combine together to give a group, then that operation doesn't matter. We do have interesting operations and combinations outside groups also, or outside addition. It's just that these properties are really like they sort of are nice when we are talking about abstract sets, so to say. So for example, closure. Why would you think closure is important? Well, because if the operation is taking you outside the set, then it's not really meaningful, right? I would rather extend my set so that at least I stay within the set, right? So closure is a very natural thing to demand, some sense. And also associativity, because I don't want to keep track of brackets while doing my operation. So associativity is a nice thing to have. I want to, yeah, when we talk about groups, I do want to talk about a nice set of examples outside the unusual things that we see. While we are talking, another sort of example that one might think of is a very natural multiplication, right? Again, this operation gives me closure because I take two integers, I multiply them, I get another integer, right? So I do have closure in this. This operation is also associative because I don't have to keep track of brackets while multiplying, right? I also have identity because I take any integer, I can just multiply it with 1 to get back that number itself, right? And it works both ways. What I don't have is inverses, right? Because if I want to talk about inverses with respect to multiplication. For example, let's take a particular number. Let's take 2. What is that number such that when I multiply 2 with itself, I get back 1? Well, that number is what we call 1 over 2, right? But this number is no longer an integer, right? Not an integer. So if I'm restricting my view only to integers, I don't have inverses. If I want to talk about inverses, what I can do is I can extend my set. From integers, I can go to rational numbers, and their inverses make sense, right? So, so yeah, let's see another sort of example of groups. It's symmetry. So it's symmetries of a triangle. Okay, so this is actually quite nice. So let's say I have a triangle. And let me label the vertices 1, 2, and 3. Now, if I ask you, what are the operations I can do on this triangle to sort of keep this intact? Like, like I don't want to cut it. Like I cannot cut it, right? But what kind of geometric things I can do so that I keep my triangle intact? So one thing is obviously that comes to mind is rotations. Right? We can rotate our triangle. And also another thing that we can do is we can reflect. So you can keep like sort of say one vertex fixed and then sort of reflect the other two vertices. Right? Those are the only things that we can do to sort of keep this figure. So let's see rotations. What we will get if we rotate our triangle. So rotations. So this is my original figure. Let's say I sort of rotate it, right? So imagine this. So what will happen is the label of my vertices will now change, right? So what was 1 before will become 3. What was 2 will become 1. And what was 3 will become 2, right? Now I can do this again, right? I can do this thing again. So apply the same rotation again. What will happen? So what was 3 will become 2, 1 will become 3, and this 2 will go to 1. And now what happens if I apply this rotation again? This is a question for audience. Just take a couple of minutes. And what we have been doing, if I apply the same operation to now this rectangle, sorry, this triangle with this label, what will I get?
The same thing, right?
The same thing that we started with, right? So if I apply this again, I'll get back the original thing that I started with. So yeah, So 1, 2, and 3, right? So there are sort of two rotations that I can do, right? Third rotation gives me back my original thing. So there are two rotations. And then let's also see reflections. What sort of reflections I can do? So the idea is, I sort of fix one vertex, let's say number 3, okay? So I fix this and I draw a line that that bisects my opposite side like this, right? And then I reflect along this line, right? So 1 becomes 2, 2 becomes 1, 3 stays intact, right? So if I apply this reflection, what I will get is, well, I already fixed 3, right? And now 1 becomes 2, 2 becomes 1, right? And I can do this. So there are 3 reflections that I can do, right? By fixing each vertex. So let me just draw them also, just for the sake of completion. So I have 1, 2, 3. Now I can instead fix number 2 and then sort of reflect like that. And I'll end up with 2 is fixed, 1 becomes 3, 3 becomes 1. And same thing, 1, 2, 3. Let's fix 1 this time. And then sort of draw this and then reflect the other two things. So 1 is fixed, 2 becomes 3, 3 becomes 2, right? These are the only really, and of course you can do nothing, right? So stay original. So that's also one operation. So doing nothing and then 2 rotations and 3 reflections, they give you 6 elements, right? And there is really nothing else that you can do. So let me just try to rewrite this in a slightly different way, okay? So if we think of our original label as, so let's take this set rather, 1, 2, 3, right, of vertices. So what was the first operation that we did? So, well, first operation, I mean, even before rotation, as I said, we do nothing, right? So as a function, you can think of this. So 1 goes to 1, 2 goes to 2, 3 goes to 3. I'm doing nothing to my vertices, right? That's first element. And then second was obviously rotation. So how did we rotate? So what happened to our vertices? Well, if you look at the first figure, 1 becomes 3, 2 becomes 1, and 3 becomes 2. So as a map, it's 1 goes to 3, 2 goes to 1, and 3 goes to 2. What was our third map? Uh, well, we applied this again. So what happened was, so 1 goes to 2, and then 2 goes to 3, and 3 goes to 1. And then there were 3 reflections, right? So 3 reflections, well, you keep one of them fixed and you interchange the other 2. So just to think of these symmetries in another way, you can think of these as really, what are these things? If you take this set of 3 elements, you are basically constructing all the bijective maps from this set to itself. And by bijective, I just mean surjective plus injective. So what we are doing is we are constructing maps or functions from 1, 2, 3 to itself that are both 1 to 1 and onto, right? By one-to-one, I mean that if you just look at any one of these maps, well, no two elements, no two different elements go to same element, right? So in other words, I don't have something like this. Like I'm not sending both of these to 3 and then this to 2. I'm not doing something like that. Each element is going to a different element, right? So that's what I mean by one-to-one. And by onto or surjective, I just mean that every element is covered. So 1, 2, 3, they all come from somewhere. I'm not missing any element. I'm not missing anything, and then all of them are going to different things. And if you just think about it for a second, so these are really all the maps, right? You can't do anything else, because if you want every element to be covered, and then you also want every element to go to a different element, then these are really all the possibilities, right? Because you can either keep one element fixed, we've already covered, and then the other two have to go to different things or the same thing, right? So that covers your identity and the 3 reflections. And the of course the second condition is that none of the elements is fixed. So those are your 2 rotations, right? So
I lost the sound. Can everybody else hear?
I got disconnected, and right before I was disconnected, everything was garbled. I see Rakvi's screen, but I can't hear her.
can you hear me now?
I can hear you now.
Yes.
Okay. Where did you lose me? I can speak again. Sorry.
You were talking about whether it's surjective and injective, both.
Oh, okay. So yeah, so what I was saying was, so if you look at this set of symmetries of this triangle that we just constructed, another way to think of this would be basically we are constructing maps from this set 1, 2, 3 to itself, right? But I don't want just any map. I want my map to be both 1, 1 and onto, right? And I was just explaining what 1, 1 means. So 1, 1 means that, so I have 3 elements, right? And I have to send it to 3 different elements. I don't want to do something like this and then this, right? So every element must go to a unique element, right? No two different elements should map to thing. And then also every element should be covered. Like I want 1, 2, 3, all of them to be in the images. Like if you look at the example here, 1 is basically missing, right? So I don't want that. So I want every element to be covered in exactly once. So that's what I mean by, so that's what I meant, that we are constructing maps from 1 to 3 to itself that are both 1 to 1 and on to. And then what I went to say after that was that if we just think about it for a second, if we want to construct maps from 1 to 3 to itself that are both 1 to 1 and onto, then there are really 6 possibilities. These are really all the possibilities that we can do, right? Because either we want to keep some element fixed, that gives us 3 reflections and also 1 identity, or I want none of them to be fixed, and that gives me 2 rotations, basically, right? So these are really all the maps. And then I was just explaining that if we just take set of all of these 6 maps, right? This set has another name. This is called S3. The capital S basically means symmetric, and 3 because we have 3 letters, we have 3 vertices. Right? So this is also known as symmetric group of 3 letters. In general, we also have a concept of S of n, right? This is symmetric group of n letters. So what this would be, this would basically be set of all 1-to-1 plus onto maps from, now instead of 3 I will have n letters, so from 1 to n to itself, right? So this is Sn. I don't want to talk about Sn now in general. I mean, this has a very beautiful theory in itself, but let's just stick to S3, okay? So but talking about groups, right? And I arrived at this example. So when we talk about groups, we are not just happy with set. We also want some kind of operation on it, right? Somehow we want to compose 2 elements, or like we saw, like add, multiply, subtract. There should be some operation, right? So what is the operation on S3? Well, what are the elements of S3? So if you just look at elements of S3, that already tells us how we can compose them. So these elements of S3, they are functions, right? They are bijective functions. And what can we do with 2 functions? Well, we can compose the functions, right? So S3, the operation is composition of functions. This is the operation. And what do I mean by composition? What do I do? So let's just take an example. So let's just take this function f, that let's just take one of the rotations, okay? So let's just take this one, 1 3 2 1 3 2. So f is my function from 1 to 3 to itself, such that 1 goes to 3. I hope this was, yeah. 2 goes to 1 and 3 goes to 2, right? And let's take the second rotation. So again, G from 1 to 3 to itself, such that 1 goes to 2, 2 goes to 3, and 3 goes to 1. So how do I compose them? What do I mean? So whatever the composition is, I denote it with F small circle G, right? And I'm composing, so this better be another function from 1 to 3 to itself. Okay. And where do I send 1 to? Well, the symbol already tells me what to do. Okay. So first I'll apply G and then I'll apply F. Okay. In the reverse order, or like in the outermost order, right? So first I'll apply G and then I'll apply F. So first I'll apply G, right? So G sends 1 to 2. Okay. And now I'll apply F. So
Rockvi, can you hear me? Your sound cut out again.
Rakvi, we can't hear you.
Can you hear me now? Can you hear me now?
Yes,
now
now I can hear you.
now you're back.
Okay. Oh, you can hear me now, right? Oh, okay. Where did you lose me again? I can repeat. Sorry.
Composite. You're talking about the symmetric group S3 and composition.
Okay. Okay. Yeah. So I was just saying that, yeah, we arrived at this example via groups, like we were discussing groups, right? So when we talk about groups, there is always a set and then an operation. So operation for us is basically composition. And then I was explaining how do we actually compose two functions. Okay. So let's just take two rotations that we had. So these are the maps, right? F sends 1 to 3, 2 to 1, 3 to 2, and similarly G is the other rotation. So how do I compose them? So I was just explaining. So if I want to look at where one goes, first I apply G and then I apply F. So G sends 1 to 2 and then F sends 2 to 1. So F of G should send 1 to 1. Okay. And similarly 2 goes to 2 and 3 goes to 3. So this is my composition, right? Similarly, what I can do is you take any two elements here, any two maps, and you can compose them in the same way. And you will get back some element of S3, right? You will get back a bijective map from 1 to 3 to itself. So we do have closure, right? And then you can also check that we have an identity, inverse, and associativity on this, right? So I would just leave this as an exercise for everyone, that check that S3 with respect to composition is a group. Okay. And I just explained how do we compose. Similarly, we compose it for any two elements. All right. So now with groups, we already saw plenty of examples and there are many more, and we will see them. We will see many more examples. But now with groups, I slightly want to move my story to rings. Okay. Like we had groups, ring also, think of it as a set. Let me call this R. But now instead of one operation, remember on groups, we had a single operation, right? A set and an operation. Now instead of one operation, I have two operations. And I'll give them a name. I'll call them addition and multiplication, right? Such that the following properties hold. So if you just look at R and addition, this is a group. Okay. So only with respect to addition, this set is a group, and not just any group. We have further an additional property that if you take any two elements of this set, and again, I would really encourage you to keep this example in mind. Keep the example of integers with respect to addition and multiplication in mind. Okay. Addition as in addition that we are familiar with, like how do we get two numbers and multiply two numbers. Further, if we take any two elements, m, and you add them, the order of addition doesn't matter, right? It's same. M plus n is same as n plus m. Like with what happens with integers, right? 1 plus 2 is same as 2 plus 1, and so on. So this is a group. If you look at R with respect to multiplication, This is not necessarily a group, right? But some properties of groups hold, right? So this set, so the following things hold. Well, this multiplication gives closure. So if I take two elements, I multiply them, I get back another element, like we had with integers, right? This multiplication is associative. And identity exists. But what we don't have, we are missing inverses, like we had with integers, right? So let's just go back to our example. So we had closure, we have associativity, we have identity, but we are missing inverses, right? So in general, in a ring, we don't impose this condition of inverses. Having multiplicative inverses is really a special thing. So we don't really impose it. Okay. So these two things. And now, since we have two operations, there must be some, like they must interact in some way, right? Otherwise, it's like saying we have two distant things and they never talk to each other, which is really weird and not interesting at all. So these two operations, they interact among each other. And this interaction is what we call distributive property, distributivity. Okay. In other words, if you take two elements, let's say B and C, and you add them, and if you want to multiply A to it, well, what do? It's the usual opening of the brackets, sort of distributive thing, right? A cross B plus A cross C. Also, B plus C times A is just B times A plus C times A. Okay. Abstractly, this is what holds. Now, yeah, it's very natural to think, like if you just see examples of integers or rational numbers or real numbers, for example, you might think that these things are so obvious, right? Like, why are we making such a fuss about them? But then there are many more interesting examples outside these numbers that one is familiar with, that these properties they are not that obvious. For example, like, let's just move slightly from numbers and let's just see matrices. Okay, so let's just see an example of matrices. So an example of ring, an example of rings. So for example, let's take 2 by 2 matrices. Okay, so let's just stick to 2 by 2 matrices. So A, B, C, D, and let's just say I want this numbers to be integers. Right? It's really an infinite set because there are so many examples. But if you just want to keep some explicit examples in mind, well, there is obviously zero matrix. Then there are some nice diagonal matrices. And then there is
You're cutting out again.
Can you hear me again?
You're back, but I can hear you, but I don't see your screen. Oh, there's your screen.
Yeah, I just shared it. But you can hear me fine, right?
Yes.
Again, sorry, where did you lose me?
You were talking about 2x2 matrices
Right,
as an
right,
example.
right. So yeah, so I was just giving some explicit example of matrices. These are really infinitely many, right? Because you have four choices and you can place as many integers as like whatever integer you wish, and really. But these are just some explicit matrices to keep in mind. But why do we, yeah, so let's just, so we want to show that these are example of rings, right? So how do we add two matrices? So if I give you two matrices, let's just pick any two. So 1 0 0 2, and then minus 1 0 0 minus 1. How do we add them? Well, we really add them like coordinate wise. So you will add the entry in the first row and the first column to the entry in the first row and first column of the second matrix. So this is really 1 minus 1 and then 0 plus 0. So like for example, so you will add this one with minus 1, and then this 0 with this 0, and then so on, right? So this 0 with this 0, and then 2 with minus 1. So what we really have is 1 minus 1, 0 plus 0, 0 plus 0, 2 minus 1. And whatever we get, 0 0 0 1 is our added matrix. So we have an addition, right? So again, just a couple of exercises. So first exercise is, okay, let me define multiplication also, and then I can give a single exercise. And how do we multiply two matrices? It's slightly complicated, but I maybe have seen this before. So again, let's just take two examples. So if I want to multiply this with itself, what do I do? Well, first of all, I take the first row and I take the first column, and then sort of multiply them like this. So 1 times 1 plus 1 times 3. 1 times 1 plus 1 times 3. And similarly, I do it for the other things also. So I'll take the first row and the second column, the second row, first column, second row, second column, so on. And I'll go on like this, right? So similarly, you can fill in the entries. So this is how we multiply two things, right? So one thing that is immediately obvious is that if you multiply or add two matrices, again, you will get another matrix, right? With integer entries. That is important. But what is not immediately obvious is that why this multiplication is associative. Addition is associative is obvious because how do we add, right? We are adding basically coordinate wise. But the fact that matrix multiplication is associative is not immediately obvious and it needs a proof. Okay. So I'll leave another exercise. Check that these set of 2 by 2 matrices, which I'll call M2Z because the entries are integers, is a ring with multiplication and addition as described above, right? So there are three things to check. First of all, you have to check that with respect to addition, it's a group. And also this commutative thing is satisfied. So this property has a name. It's called being commutative or commutativity. Second thing that you have to check that with respect to multiplication, it's almost a group. So it satisfies these three things except inverses. And then like there is this distributive relation between addition and multiplication. Okay. Now we can get more examples out of matrices like this, like more examples. There is no reason to stick to integers. you can take you can take entries in rational numbers, entries in real numbers, entries in complex numbers, right? These are also rings. And why just 2 by 2? You can in fact take 3 by 3, or even better, take n by n with appropriate entries of your choice, right? They will also be examples. So after you're done with previous exercise, and if you want to try this, so check that in fact n by n matrices, where n is now any size, not just 2 by 2, but anything. Check
Can you hear me, Rakvi? Your sound broke up again.
I can hear you. Can you hear me?
Yes, you're back now, but your sound broke up a little while ago again.
Oh, okay. Sorry, I'm not sure what is happening today, but where did you lose me again? Sorry.
You were talking about generalizing the example to
Okay.
include rational, real, complex entries or arbitrary n, and then you posed some homework challenges.
Yeah, I just said that you can check that if you take set of n by n matrices with integer entries, is actually a ring. And the proof will be same for Z, Q, C, or R for that matter, right? So it's a good exercise to try. Yeah, what I was saying was that now that we are familiar with terminology of groups and rings, and like this is not the only class that we will discuss groups and rings, and like we will be discussing them in coming lectures also. But finally, I can talk to you about fields. Okay, so what do I mean by fields? So just to give a definition, a formal definition, a field, let me call this F, is a ring. Okay, so you know what a ring is. Such that, well, so I've already said it's a ring, right? So there is multiplication defined on it, right? So if you take this set with respect to multiplication, this is an abelian or a commutative group. Let me not use the word abelian, but commutative group. And what do I mean by commutative group? Well, we already know what a group means, right? Commutative, I just mean that this property is satisfied, right? So if I take two numbers, the order of multiplication doesn't matter, right? N times n is same as n times n. That's what I mean, right? And we already know an example. We have already seen an example. Let's go back to integers, okay? So we already saw that integers actually form a ring, right? But what is missing from it being a field? Well, what is missing is that when we restrict ourselves to multiplication, we don't have inverses, right? 2 doesn't have a multiplicative inverse in integers. Because what is multiplicative inverse of 2? It's 1 over 2. It's a rational number, right? So Z doesn't suffice. I have to go to rational numbers. So if I think of rational numbers, well, obviously there is addition and multiplication defined. You can add and multiply two rational numbers. And now the problem of inverses is solved, right? Because if I take m over n, let's say non-zero, then it already has an inverse, right? And it works both ways. So this is a field. Just a technical point here. I don't want F, rather I want F. I don't want 0, right? Because 0, it doesn't make sense for 0 to have a multiplicative inverse. So I want all.
Your sound is going again. Hello, can you hear me, Rakvi?
I can. Can you hear me?
Yes, yeah, we lost you again. Sorry.
Okay. No. You don't have to apologize. I don't know what is happening. I'm practically doing nothing to my
Hello,
apparatus, and
hello, Rakvi.
yes,
Have you joined from the same device you were writing on, like the iPad?
y- yes.
Actually, what you can do, like this happened in our online class year also. So join. So like keep writing here. I mean, join in your Gmeet and write here, and keep that mute and join from another device and speak from there. So there is too much load in
Oh,
that.
okay.
Yeah.
Okay. Oh, thanks for that tip. Okay. Yeah, I guess it's almost time, so I'll do that from next time onwards. Okay. Um. Yeah. Thanks for the tip. Okay. Yeah. So basically, just to repeat what I. So we know. Yeah. If you missed my voice, sorry. I just introduced fields, right? So field is a ring such that if we take all the non-zero elements, so now with respect to multiplication, it's a commutative group, and I was just showing some examples. Okay. So from next class, what we will do is uh, we will actually talk about finite fields, because this is very important, because when we will go back to discussing elliptic curves after next lecture, so the lecture on, so today's 10th, right? So lecture on 24th, we will start discussing about elliptic curves again. So there finite fields will play, like we'll talk about finite fields a lot, right? So next class we'll talk about finite fields. I'll introduce them, what are they, and then I'll sort of discuss some basic arithmetic on it. So yeah, so just wanted to end there. Thank you. Yeah, if there are any questions, just let me know.
Yeah, there was a question, but I think it's jumping the gun a bit since we haven't talked about finite fields yet.
What's the question?
It's whether the ring over a prime squared, the nature of that ring.
So it's
Oh,
about the
right.
difference between FP and FP squared.
Oh, FP and F. Yeah, we'll talk about FP next week. And FP square is basically, so I can just talk briefly about it. So basically, what happens is, so FP. So let's just take a specific P, right? F3. So this is a finite field of 3 elements. And F9, which what I'm assuming you're talking about, is a finite field of 9 elements. Okay. And this is not what one usually thinks. So F3 is like basically Z mod 3Z, right? So we take congruence as 0, 1, and 2. F9 is not Z mod 9Z. It's actually a vector space over F3 of degree 2. Okay. So this is a field extension of F3 of degree 2. So in general, if you have a finite field in the base and you take a degree R extension, what you will get is FPR. Okay. Next class. Yeah. I just wanted to set some examples and some terminologies here so that when we talk about fields next time, it's not, yeah, it's familiar to everyone.
Thank you, Rakvi. Yeah, we're running short on time. And thank you to the person who's just suggested using a phone for the audio.
Yeah, I'll do that from next. I think if I remember, I did that last time and there were no issues, but today I just thought I'll use my iPad, but it was breaking a lot. So yeah, thanks, Agnew. I'll do that from next time. Yeah.
Yeah, these things happen sometimes, even in the other sessions as well. I don't know whether this is a Google setup, but yeah, it's actually maybe if we follow the let's follow the tips with the suggested by our friend here.
Yeah, that was a
hopefully
good
could solve.
suggestion.
Yeah.
I'll
But
do
don't
that.
worry about it. These things happen.
Sure.
Yeah. So I have actually, before everyone goes, I have some something to share.
Okay.
So my colleagues have been suggesting, obviously, because of our courses, whether we should add for any of our courses, whether we should add some sort of a chatbot to aid in the studies and these things, Now, because we don't want to build any chatbot from scratch to start with. So the idea was, could we leverage something that already exists as a starting point, and then if there is such a demand for custom chatbots, maybe with the help of community members or maybe with ourselves, we can build a custom chatbot. Yeah. So we are using my colleague. I have someone who kindly offered to create a chatbot using OpenAI ChatGPT for this course. So let me share with you here. I'll share the URL with you. Unfortunately, I think you have to have the how do they call it? The plus. I didn't have it either, but this guy, this friend, invited. So here's a link. You can see, and I will be adding some resources into it, some resources so that obviously it can make use of RAG, retrieval augmented generation, to try to compose useful answers. So let's test this. Let's say, what is a cyclic group, for instance? This is something that you'll come across.
Sorry, I think I missed what you said before. So, like, is this ChatGPT or some other
This is
version?
ChatGPT, actually, yeah.
Is this like paid version of ChatGPT or like one that is freely available?
This is actually, you need to have a plus. This is nothing to do with us. The person who did this is part of my the company. He just suggested maybe we could create a chatbot for specific courses. In this case, for this elliptic, for your course, Rakvi. But we didn't want to, obviously, to build our own custom to start with. So he suggested to use ChatGPT. But unfortunately, you need to have, I don't know why, hopefully OpenAI will change this to make it like freely available, because we are certainly not interested in monetizing this, to make it like the time we wanted to make it available for free. But unfortunately, you have to have the OpenAI plus or something to access it. Yeah. So,
okay.
But the link, the link is there.
Can we trust ChatGPT on the mathematical rather than linguistic questions?
Yeah, well, that's a good valid question, But hopefully with more resources. I'm actually very skeptical about this, but this is just for the newbies, I guess, mostly for to try to maybe have some extra toolkit that will make people simplify some of the concept that Rakvi will be presenting formally. Yeah.
From what I've heard from my friends, like personally speaking, I have actually never used ChatGPT for anything mathematical. Uh, I used, I think, when there was a lot of hype, I just used it for like I just asked some questions that were mostly like literature or from poetry or something, like subjective things like this. I never used it for anything mathematical. But from what I heard from one of my friends, so he was teaching, I think this was last semester, he was teaching some advanced level 4 class in analysis or something. I think harmonic analysis or something like that. And he was using a paid version of ChatGPT, and ChatGPT was actually able to solve his homework problems, which were,
Okay, interesting.
I mean, I would assume they were at least some level of sophistication. So,
Okay.
yeah, I thought that was quite interesting. Yeah.
I will ask our friend here, my colleague, to keep adding more resources into it to see whether it can, scan through the content, using RAGs to see whether it can compose useful answers at the community. But so the verdict is out, George, indeed, whether this is useful or not. But yeah, this is just, something I thought we could just add up here. Unfortunately, it's pity that OpenAI doesn't, you need to have the premium, the plus thing, which I think they should actually allow the people who create these GPTs to actually say, we want this for free, because for us, we are just, this is just some sort of an idea that is just we thought whether it could be useful, especially for the newbies who might be intimidated with some of the stuff, maybe, something more.
I mean, I would definitely agree with checking everything, especially with something like ChatGPT, because even if you use some sophisticated platforms for these computations, like let's just Sage or Python or even Magma, like I have encountered errors even in Magma. So I would not trust ChatGPT without double checking anything. So
yeah, absolutely. Absolutely. And I guess it's also, there could be a way of hacking to use it. It's actually a way of, seeing when it says anything that nonsense, then maybe you can, people, as a way of actually solidifying the knowledge, you could actually say, okay, here's an answer that ChatGPT gave. This is wrong. It should be this. So,
yeah.
So that could be a way. But anyway, this is just optional, obviously. I wanted to just share. Unfortunately, obviously, because this is, it requires the plus thing, it won't be available to all of you. But yeah, I'll ask my friend, my colleague, to keep adding resources to see those of you who want to use this just as a thing.
Yeah. Bob Miller in the chat says that he's tried it and it can count, but it can't solve more sophisticated problems that you need to double check. And furthermore, Bob tried it on quantum questions and it returned an answer that looked good but was total BS.
Yeah. The so-called hallucinations. Actually, on the quantum thing, I'm actually thinking to do something on that front as well. Yeah. So I will share that in Carlos's course as well, another chatbot, to see whether it's any use, especially for the newbies. Yeah. But nevertheless, if it's always a good, I guess the positive side of it, even if it spits BS, at least you can solidify using your knowledge to spot that it's BS. That's already a good thing. To use ChatGPT to enhance your understanding of a topic, I guess. So that could be a positive way of using it. Yeah.
So I have a question from Agnivo that I think I can answer. So his question is, like, while working in algebraic number theory, arithmetic geometry, how did you come across ECC as a field? Research-wise, it will be good to know. Well, research-wise, I mean, I have not done any research in cryptography, so to say. My research so far has mostly been in elliptic curves and I've also worked in isogenies of elliptic curves, but nothing like cryptography, like nothing from cryptographic point of view. I'm familiar, like whoever works in elliptic curve is familiar with elliptic curve cryptography as one of the applications. So I'm familiar with the theory of it. So that's why, like, when Bambode, like, we were chatting and Bambode said, like, would you like to give this a course? I thought this would be a nice opportunity also for me to, like, brush up some of my knowledge on ECC, right? Like I read about it some time ago, like, just as a student, like, I was just curious about it. But to teach it to a group of people is an entirely different game, right? You yourself learn a lot of things. So I thought this would be a good opportunity to brush up on my knowledge of ECC. So that's how I am doing this. But like, if you're talking about anything research wise, I haven't done anything in cryptography. So
Yeah,
but
this is
I'm
actually
looking forward to it. I mean, I'm looking forward to good problems. And
it's a nice segue for actually a good question, because one of the things that we will be doing, I will be inviting cryptographers in the industry to come and give a talk about the
that would be
application,
awesome,
the
actually.
application
Yeah.
side, especially in familiar protocols, that are leveraging elliptic curves, So yeah, you will have
I mean,
we'll have
if they can actually share some nice demos and everything, that would be
Yeah,
really awesome.
absolutely, yeah. So okay, in that case, maybe I'll stop recording so the video doesn't go too much, and then maybe we can close, or anybody who wants have any questions or something, they can just feel free to come if they were not comfortable to come in while it's recording.
Yeah, I just want to
Okay.
ask